Most classifiers are happy with any line that splits the two classes. Support vector machines are pickier. They hunt for one very special boundary, and the idea behind it is beautifully simple. Here are two classes, red on the left, green on the right. We want a line that keeps them apart. And here is the catch. Many different lines do the job. All of these separate the colors perfectly. So which one is actually the best? They cannot all be equally good. The SVM answer is this: do not just separate the classes. Push the line as far as possible from both sides at once. Imagine widening an empty street between them until it is as wide as it can be. That widest possible street is called the margin. A wide margin means a new point has lots of room before it could ever be misjudged. The boundary runs right down the middle. Now look closely at which points actually touch the edges of the street. Just a few. These special points are called support vectors. They are the whole secret. Here is the surprising part. Only these support vectors hold the boundary in place, like tent pegs. Every other point, all the way in the back, could move around, and the line would not budge. The edge cases are all that matter. But real data is messy. What if one red point wanders deep into the green side? If we insist on a perfect split, the street would have to shrink to almost nothing, bending around that one stray point. So SVM does something wiser. It lets a few points sit inside the street, or even on the wrong side, and just charges a small penalty. A setting called C decides how strict to be. A little forgiveness keeps the street wide and the model calm. That is a soft margin. One last idea, and it is the clever one. Sometimes no straight line can ever work. Picture one color trapped in a ring of the other. A straight street is hopeless here, so the kernel trick lifts the points into a higher dimension. Give each point a height based on how far it sits from the center. The trapped inner color sinks low, the outer ring rises high. And now, in this lifted world, a simple flat plane slides right between them. The exact same trick as before, just in a richer space. Bring that flat cut back down to the original picture, and it becomes a smooth, curved boundary, a circle, wrapping neatly around the inner group. Straight in the lifted world, curved back home. So a support vector machine finds the widest street between classes, leans on just a few key points to hold it, forgives a little mess, and can even bend through a hidden dimension when it needs to. Pure geometry, doing the work. SVM draws a careful boundary ahead of time. But what if a model did no work at all up front and simply asked the nearest neighbors at the last second? That is next.